Good morning, everyone, and delighted to be here at the Asian Winners School and to see all of you. It will indeed, as far as I can tell, be an exciting school with an incredible set of lectures. This one probably won't be the best, I can assure you. I was hoping very much to prepare a chalk talk, which is the best way. Over the last few days, the last week, a incredible conference celebrating 10 years to this wonderful institute. And it's been so full of great talks, which I recommend that you watch. They'll all be online, and really some wonderful talks. And I didn't have time to prepare what I really would have liked to give, which would be a pedagogical chalk talk. Instead, I'll have to resort by and large to slides that I've used in previous talks. But there will be 4.5 other hours of talks on the SYK model given by my collaborator, Vladimir Rosenhaus, whom I've been working on for the last 2 years on the SYK model. And anything that I do badly or leave out, he will fill in, I'm sure. So let's proceed. The SYK model stands for SACHDEV-YE and KITAEV. SACHDEV and Ye are condensed matter theorists who, over 20 years ago, 25 years ago, I think, introduced a very interesting model of fermions living sort of at one space-time point, you might call an atom there's no space, interacting in a very interesting way. The motivation of Subir SACHDEV was to find a soluble model which had a non-trivial quantum critical point. The idea is that long-range behavior of quantum systems can have non-Fermi liquid type behavior that might underlie things like high-temperature superconductors, but very little is known about such critical points, and any soluble example is instructive. And there was quite a bit of work on this model in the condensed matter theory community by SACHDEV and others. But the model, by and large, was forgotten, and remarkably, particle quantum field theorists never paid any attention to it. But Alexei KITAEV did, and when he got interested in the black hole information paradox during 2 years which he spent at the KITP, and thought that this might be a good example of a quantum mechanical system in one dimension, just time, which would be holographic in the ADS-CFT sense to a two-dimensional theory of quantum gravity. And he simplified the model to some extent, analyzed it, particularly focusing on chaos, the chaotic behavior of this model, and arguing that it behaved in a way that was characteristic of systems which are holographic to quantum gravity. And that aroused a lot of attention, since it's always nice to have a soluble model of holography, and this appears to be one, and it has been studied extensively by many people over the last few years, and that is roughly what I will try to review. So one of the most interesting aspects of this, the SYK model, which attracted me, is that it's a new class of so-called large N theories. And I'll briefly review the kinds of large N theories that have played a very important role in quantum field theory and condensed matter theory and in holography over the years. And SYK is a new class which has been overlooked. And I and others have felt that a new class of large N theories is bound to be interesting, not necessarily for its original purposes, but who knows what, studying in detail. As I said, it's a one-dimensional model, so it's quantum mechanics. There's no space. It couples Majorana fermions, real fermions, half of Dirac fermions, 2 dimensions, half of Dirac fermions. And as you'll see, the interaction is Q body, where Q can be 4, 6, 8, infinity, coupling Q fermions or Q Majoranas at a time. And one of the unusual features, probably the reason that quantum field theorists didn't pick up on this model for years, was that the interactions are random, quenched random numbers. Quenched just meaning that they're given once and for all by a set of numbers chosen from, say, a Gaussian distribution of couplings. This is quenched random interactions are commonly used in condensed matter to describe disordered systems where the couplings of, say, spins in a medium which is full of defects vary from point to point in a way which one can't control. And in calculating observables, one therefore only tries to calculate some kind of average over a reasonable probability distribution of such constants. So that's a bit unusual in quantum field theory, where we typically, assume homogeneity and fixed couplings, and we'll be discussing that a bit. The other interesting thing about this theory is that it will have a critical point, a point which exhibits scale invariance, but actually even more than that, the theory from the beginning is diffeomorphism invariant. Diffeomorphism invariant, much like quantum gravity, that's broken by the interaction down to the conformal group in one dimension, which is SL2R. And it's soluble. Maximally chaotic, that was the observation by KITAEV that led to the conjecture that it's holographic. There's some kind of gravity theory in 2 dimensions. Now, 2 dimensions is a particularly trivial but subtle case of quantum gravity where there are no dynamical gravitons, but still there is some dynamics in the gravitational space-time. And one can discuss black holes in this background, in a particular background, when you couple the gravity to a dilaton or to a scalar field. And And in fact, that ADS solution, sorry, with in a background which has a negative cosmological constant, which by general law we believe might be holographic to a conformal field theory in one lesser dimension, and that appears to be the case, that this model of quantum mechanics in one time, no space, is holographic, say at finite temperature, to a black hole in gravity in 2 dimensions with a negative cosmological constant coupled to a scalar field. So let me briefly say a word about large N theories in general. SYK, as I said, is a new class. The old classes that have been used very efficiently over the last 50 years in quantum field theory and in condensed matter, many-body theory, are vector models and matrix models. The simplest being vector models. So, in general, what that means is that we have a class of quantum field theories with some field and an index that runs from 1 to n, and that this field forms a representation. It's a vector, but the dynamics is invariant under some SON or SUN symmetry group. So the Lagrangian might be, for example, standard kinetic term in some number of dimensions with some interaction which is only a function of phi I squared. Now, in quantum field theory, we would like to calculate the partition function, the generating function, with if we add sources of the let's work in Euclidean space-time, and so Lagrangian written here is positive definite, and we have like to calculate the partition function, maybe adding a source in order to generate the correlation functions of the dynamical variables. Now I'm suppressing space-time labels and maybe even derivatives. Most of the features of large N emerge already in 0 dimensions, where one, as I will here, is just, well, there might have been a mass term here, where one is just doing an integral. Now, in quantum mechanics, in many-body theory, and quantum field theory, we often, just about the only thing we can easily do is expand such an integral in powers of h bar. And what we're doing in that case, of course, is doing a saddle point analysis of this multidimensional integral. And we generate a sum of Feynman diagrams. Now, so ignoring the source term, we just have vacuum diagrams, and which, as you know, are the exponential of connected diagrams. And let's take a simple case I'll set h bar equal to 1 and consider now just an integral of phi I squared and some function of phi I squared, summed over in this over. If we look at this integral, having dropped the h bar, we note that phi I squared is a sum of n variables. So as a function of n, it kind of behaves like n. And therefore, for large n, we might look for a saddle point even for finite h bar or finite coupling. Expansion in powers of h bar is actually an expansion in the couplings. For example, if we have here a coupling, the simplest phi 4 theory, we can scale out by taking phi squared to 1 over g phi squared, 1 over g squared phi squared, take out an overall factor of 1 over g squared. So an expansion in h bar is like an expansion in coupling. And Feynman diagrams, which summarize perturbation theory, are really a weak coupling expansion. So typically, this will be a sum of diagrams, vacuum diagrams, like this, and then perhaps like this, and so on. This is just one field going around in a loop, has no powers of the coupling, but here there's a g squared, and so on. Next order, we get diagrams like this, which is of order g fourth. So that's ordinary perturbation theory. We evaluate that, in this case, by using as a propagator. The propagator here has labels I and j for our fields. The propagator is just, in the case of 0 dimensions, just delta ij. And the vertex here is complicated because we can contract these indices in different ways. But it's of order g squared. Now, perturbation theory is fine, and people analyze perturbation theory and quantum field theory all the time, use it to calculate lots of physical processes. But the general problem in a perturbative analysis of quantum field theory, many-body theory, is that in general, these series diverge. There might be signs, but no matter how you choose the sign, a series like this has 0 radius of convergence, and this is always the case in any quantum field theory if you just expand in powers of the coupling, already in quantum mechanics. That makes the perturbative series totally ill-defined without some kind of non-perturbative information. Nonetheless, we do calculations in QED and get answers that are correct to 1 part in a trillion because it's an asymptotic series. So as long as we only consider the first n terms where n is much less than 1 over g, which could be quite big, or g squared of order 1 over 137, we can get a very good answer, but at some point it blows up. So instead, we consider for large n theories the behavior of this generating function, or the vacuum energy here, as n goes to infinity, and keeping g fixed in such a way that each term here is the same order as a function of n. For example, this first term has a propagator, which is just delta ij. There's no integral, so this is just 1, but they're n diagrams, so this term is of order n. Which is not surprising. This is the vacuum energy of a system with n degrees of freedom. The energy is proportional to n. This term, there are two ways we can contract these indices, and again, we represent that by index lines. So here, this is phi I times phi I, phi j times phi j with summation convention, and we can contract I with I, and that would correspond to this term, where I goes here and j there, or we can contract I with j with a delta ij, and the index loop then looks like this. They both have a factor of g squared, but this one gives n squared, and this one gives n. So clearly, if we want to, this one gives, yes. If we want to take n to infinity and keep a term of order n, like the first term, we should choose g squared to be proportional to 1 over n. So g squared n equal to a constant. In which case, this term is down by 1 over n. It's of order 1, whereas this term is of order n lambda. So instead of getting 2 diagrams, we only get 1. And it's easy to see that to kth order in perturbation theory in powers of g squared or in powers of lambda, so this is now lambda over n, the only diagrams that will survive will be iterated bubbles. We can just add bubbles anywhere here. Every time we add a bubble, we get a new factor of n and a new factor of g squared or a new factor of lambda. So the general term here will be lambda to the k times some coefficient. Sorry, times n. That greatly reduces the number of graphs, and it's easy to see that in general power series like this, overall n, sum of c to the k, lambda to the k, and c to the k behaves like some 1 over lambda c to the k. So the terms grow geometrically and not factorially. And such series, of course, are convergent for less than lambda c. So this is typical of large n approaches. And you can see that the advantage to begin with is that large n perturbation theories now converges in some range of couplings. And you might go to beyond that by analytic continuation. And so it gives you a well-defined expansion, convergent expansion in powers of the rescaled coupling. The other thing about large n expansions is that we all know that coupling constants in quantum field theory, g squared, tend to run. They're not necessarily fixed in all regions of, so that these expansions are totally often uncontrollable. I mean, the ordinary perturbative expansions, whereas n is a number, it's not a dynamical quantity. And finally, large n for quantum field theories or quantum mechanical systems, often even for rather small values of n, so as I said, this gives an expansion n times some function of lambda, and they're corrections of order 1 times another function of lambda, and so on. And these expansions in powers of 1 over n can be much better than the perturbative expansion itself. It's easy to calculate the first term. It's essentially a geometric series. Geometric series are easy to calculate and often exhibit the qualitative features of the exact theory. You don't lose necessarily physics. So whether you can extrapolate the large n behavior to finite n is tricky for small values of n, but for n large enough, you capture the full physics often with small corrections. Okay. Now, so if you try to summarize the graphs here, you can see that the general structure is you draw a bubble and attach bubbles in all possible ways. How do you sum such a thing? Well, perhaps the easiest way is to cut this diagram and look at the perturbation expansion for the propagator, which you can see is a sum of a free term. If I cut this, first interaction, and then graphs like this. Now, these are all so-called connected graphs, right? One particle irreducible. Whereas here, you can have graphs like this, which, well, you can have here too, sorry. So this is the full propagator. You have graphs like this, and so on. And let's call that sum the Green's function, as usual, a two-point function. In general, you can see that the sum of graphs really says that the two-point function consists of free propagation, and then all graphs that can't be cut into two, so-called one-particle irreducible, and so on, iterated one-particle irreducible diagrams that can easily be summed by a geometric series. And the one-particle irreducible graphs that can't be cut into two pieces by cutting one line consist of things like this, where you this would be the simplest example, where you have a bubble, and then here you put in everything that consists of one particle going into one particle. So you put the full Green's function, G. So in the zero-dimensional case, these are just functions of lambda. Okay? This is 1, and this is sigma, sigma squared, and sigma is just the first term in G, so that's also 1, and so on. And it clearly is an algebraic equation, which you can solve. G equals 1 over, and I really should put here a lambda, 1 over 1 minus sigma, and sigma is just G, lambda G. And you can all solve that equation. It's a quadratic equation. The branch cut singularity, which is why its expansion in terms of lambda has a finite radius of convergence. If you were to go to higher dimension, you would have integrals here over, say, in momentum space, or the momentum flowing in this line, and you'd get a coupled set of integral equations, but it's still quadratic and they're easily soluble in any dimension. Of course, the behavior of these functions in higher dimensions, you know, is tricky, and there can be ultraviolet divergences, and there can be multiple solutions. It's a quadratic equation, and you can, but it's always soluble, at least when you introduce cutoffs to deal with the ultraviolet divergence. And large N vector theories have been used to study critical behavior long before one understood the general theory of critical behavior in the renormalization group. Have been extremely historically useful and continue to be so. That's vector theories. The second class of theories so any questions about vector large N expansions? Yes? Disconnected, it's just how the lines come into the vertex. As I said, the vertex with I want to be careful, I, J, K, L has a variety of terms. Delta I, K, delta J, L, plus delta. So we've drawn delta I, J, delta K, L, and there's a third possibility. And I write them like this, or like this, or like this. So these are all index lines. Sometimes we put a vector on them. If these are complex fields, then there's an orientation. And I'm just counting how the indices are contracted. So among the various ways we can contract the indices, these are the ones that get the 2 factors of n, and this one only has 1 factor of n. Okay? So I've separated a bit these lines, but they're really at a 4-point vertex. Now, yeah. Sorry? No. Well, I don't know of any. There are large N theories. So the large N theories that are holographic and they have been studied in 3 dimensions so large N theories of quantum field theories in 3 dimensions are a classic, well-studied system, especially for people interested in critical behavior, because the world is 3-dimensional and we look for phase transitions and second-order phase transitions, which at the critical point are described by invariant field theories, and those, according to our understanding, should be dual to some kind of quantum gravity, holographic. But it appears that they are dual to a kind of a generalization of quantum gravity in ADS space, which contains, in addition to massless gravitons, an infinite series of massless higher spin particles, and are not very well understood. Whether those systems are maximally chaotic or not, I don't think is known, but they might be. They're a little too trivial because they're essentially, turns out, integrable or free field theories in a sense. So the dynamics is not that interesting, but it could be. It's just there are other examples in higher dimensions. Much more interesting case of large N theories that has dominated quantum field theory and string theory are large N matrix theories. And large N matrix theories are very different. And there the dynamical variables are matrices. The dynamical variables are, let's call them, say, M. They have two indices. And again, we consider dynamics that's invariant under some ON acting on these indices. So we might have Hermitian matrices here, the adjoint representation of SUN or of ON, and the Lagrangian is something, again, let's work just in 2 dimensions, trace of M squared. It might be the trace of M squared is invariant. Say M well, let's take M to be complex, is a invariant under U. The unitary transformations, UN, and this would be the kinetic term, and we might have in general some function of M adjoint. Now, we have matrices, the trace of a matrix, n by n matrix is of order n. So again, this term we expect to be of order n, and therefore, we take the simplest term, we would again put here something like g squared lambda over n, m adjoint squared. Anything here, right? So this, again, the trace of matrices is of order n. There's sort of for a large n outside. And I'm interested, again, let's say in 0 dimension, in calculating, say, the partition function where I integrate over all matrices, Hermitian matrices with some measure of e to the minus L. Now, in this case, one can't play, okay, again, the dynamical degrees of freedom here are Mij. I can represent the propagator by 2 index lines, I and j, opposite directions because this is just Hermitian. This is a product of fundamental times anti-fundamental. And the interaction here has the indices, you can see, contracted in the following way. So I have a product of 4 matrices where I identify the adjacent indices. So this is the diagrammatic representation of this kind of interaction. And we can do the same kind of diagrammatic analysis of the perturbation expansion and powers of the coupling that we did here. So for example, the correction to the vacuum energy, which is now of order n squared, since each index line is summed over. There are n squared degrees of freedom in an n by n matrix. So the first term is of order n squared. And the second term is, again, a bunch of different ways we can contract indices when we add an interaction. And diagrammatically, I can represent that as graphs like this, which is of order 1, 2, 3, n cubed times lambda. So I should choose lambda to be of order 1 over n. I should define it this way. And then this graph will be of order n squared, same as this. But for large n, I can throw away lots of other graphs like this. What do I want to throw away? I want to throw away something. I want to throw away. Well, actually, in this order, there's nothing I can throw away. But in higher orders, what you can easily see is that any graph that can be drawn like this will contribute something of order lambda to the k times n squared. But graphs that have the lines crossing over in some way that can't be drawn on the plane, non-planar graphs, will be down by powers of 1 over n. And it's a famous result of 't Hooft that this can be written as a sum. This has an overall n squared, and a sum over g of functions of lambda times 1 over n to the 2g minus 2g, where g goes from 0 to infinity. And that g labels the genus, the number of handles of a two-dimensional sphere that is triangulated, by the dual graft of this graph. Now, I don't have any time to really explain how that works, but this is a remarkable expansion. One, it tells you that if you take large n, you're considering a very small set of graphs. It's not a geometric series. It's a sum of planar diagrams. But it's much smaller than the sum of all possible diagrams. And again, the number of terms in this expansion of f for g equals 0, or for any finite g, is geometric. It doesn't have an essential singularity. And so there's some hope of being able to calculate this in each sequential term. And furthermore, the kind of diagrams that survive have something to do with triangulations of two-dimensional surfaces. Kinds of diagrams that survive in this vector model look sort of like, if you draw lines through the center of these circles, branched polymers. Whereas here, the graphs that survive look like various ways you can take a sphere and triangulate it, a bunch of triangles. Now, that made matrix models very interesting from the point of view of many different points of view. One was the ability to count such triangulations of a sphere, but also in the limit where you approach critical point and the terms here with a more and more larger number of triangles dominates, to try to represent the sum over two-dimensional geometries and thereby make a connection perhaps to string theory. And in fact, this realization that the sum of planar diagrams or diagrams on a Riemann two-dimensional surface of arbitrary genus, this kind of large N expansion that Hooft made in the context of QCD, or large N Yang-Mills theory, and suggested strongly, we already had reasons to believe that QCD with confining flux tubes might be represented by a theory of strings, but this is another way of looking at it. And there has been extensive analysis of many, many matrix models of this type with lots of enormous amount. In fact, SACHDEV-YE and Edouard Brizard have a wonderful book about this thick, 700 pages of reprints of 20 years of papers on mostly on matrix models. And it's, if you haven't studied this, I strongly recommend you to study this for a variety of reasons. String theory, one of them, but this is hard. In general, there is no obvious way of calculating these functions. So for ordinary integrals like this, with one matrix, you can easily solve it by expressing this integral in terms of not n by n matrices, but just the eigenvalues. Since this is an invariant function, this is just the sum over lambda I squared, lambda I, the eigenvalues of m, and this is, I really want this outside, right? I want the trace squared in of some potential, which depends only on the eigenvalue. And so these integrals can be done in just about any case. But going beyond one matrix model, there very little is known in general. And a theory like QCD has an infinite number of matrices, gauge fields, one at each point in space-time. So in general, large N matrix models, although fascinating, the large N limit of supersymmetric Yang-Mills theory, we believe, is what is exactly dual to 2B string theory and ADS background. But in general, except for special cases, can't be solved in general. And now let me come to, finally, I can see, this is what happens when you don't have time to really prepare. So matrix models, planar diagrams, let me come to SYK, who's Lagrangian Hamiltonian, I'll write down in a moment, but there it turns out that the kinds of diagrams that survive are what are called melon diagrams. And here you see what you do are continually add bubbles. Here you have all these circles, these two-index diagrams, which give you a planar diagram on the plane. Here you have something which looks like vectors. The lines are single-valued, but the set of diagrams is not gotten by adding bubbles, but rather taking each line and converting it to a a bubble, a melon like this. So they have been called melonic diagrams. And from the point of view of duality, well, these diagrams were very interesting, as I said, in discussing critical phenomena. The critical points, field theories which have such a behavior are perhaps dual to these kind of strange quantum theories which have many higher spin massless particles and gauge degrees of freedom, which we don't understand very well. These theories, the critical points of such theories are presumably dual to critical string theory in ADS. And these theories, which will have a critical point, are perhaps dual to some other theory of quantum gravity, which we understand just a little bit of so far. These are the ones that we've been studying now intensively for 20 years, and the dual theories, string theory and ADS. They are characterized by string theory, which has, in addition to light gravitons and massless particles, many, in fact, exponentially increasing density of massive states, and are very complicated, viewed that way, but luckily we have a well-known theory of critical strings, which we can analyze in the dual bulk. This theory, as I said, is simpler. There, in addition to the graviton, the gravitational degrees of freedom of the dual theory, have an infinite number of particles, but they're all massless and degenerate, and it's very hard to understand such theories in general, even though they're quite trivial in their dynamics. And here, one of the big open questions, or certainly the one that I've focused on, is what is the bulk gravitational theory and the degrees of freedom beyond just those of gravity? This was a question. Somebody had a question. Yes. Yeah, so, by the way, another way of saying all this is that in these large N theories, you, in effect, are doing a quantum you're doing an expansion around a trivial, non-interacting theory, and N plays the role of H, 1 over H bar, and the leading term, in effect, describes a classical limit of this theory. In quantum field theory, there are often there are many different kinds of classical limits, H bar or 1 over N. So in the case of matrix models and string theory, the large N expansion of Yang-Mills theory gives you some kind of theory which leading order 1 over N is classical theory of something. And in the case of supersymmetric Yang-Mills theory, we know what that classical theory is. It's the classical theory of strings, critical strings in the de Sitter space times a sphere. Here, we don't really know what the classical theory for large N is, and what describes this tower of massive particles. So anyway, finally, this is the Hamiltonian of the SYK model. It is a vector theory in the sense that the degrees of freedom, which are Majorana fermions, have an index, a vector index. They're in the fundamental representation they're real, Majorana fermions of ON. The couplings, JI, so this term breaks that symmetry for random J's, but you regard these couplings as random quenched couplings. If you choose them from a ON invariant ensemble, the theory on average will be ON invariant. So these are Gaussian random, large N, everything is Gaussian, ON symmetric. And this theory indeed is soluble for large N just by doing the kind of diagrammatics I did, except summing the melon diagrams that survive, with the result that one finds indeed in the infrared for large times or low energies a conformal invariant fixed point. Actually, one of the subtleties of this theory is that conformal invariance is broken. You can't sit exactly at the conformal invariant point, and maximally chaotic. Yeah, anything is, for large N, it doesn't matter. Anything is Gaussian. That's called the law of large numbers. So, unless you're interested in the 1 over n corrections, it doesn't matter. I'll get to that. It's maximally chaotic in the sense that the Lyapunov exponent of that tells you how things, it doesn't matter. For large N, it's independent. Everything. Now, J comes in, J squared. Doesn't matter what the coupling is. So, again, you analyze the Feynman diagrams as we were doing in other vector models. This is the simplest Feynman diagram. You have to go to order J squared. So in this diagram, I have a vertex coupling 4 of these Majoradas. The indices are all different. If 2 of them were the same, chi squared is 0. Chi commutes with it. Or chi squared is 1. But so the indices, these are anti-symmetric in all indices. You drop the diagonal terms. So all the indices are different here. So I comes in, and you goes into KLM with a coefficient JIKLM. And here you have that J. And here you have another J. But when you average over the ensemble, or for large N, it doesn't matter, it self-averages, this had better be JIKLM itself. That means that in this vertex, again, you have the same coupling, and so I goes out. That's a sign that you've preserved the symmetry. I goes to I. It doesn't mix with J. And this correlation, and then you get the sum over all values of KLM. So that gives you a factor of n cubed. So if you choose this to be delta I prime, etc., times J squared over n cubed, you scale things in this way, you'll get a J squared over n cubed from this diagram. And that's represented by this dashed line, which enforces that all the indices here be the same as here. And you can then analyze higher diagrams. This one is of order J squared. There's another way. Well, here's that's a melon, which we just draw like this. If we go to higher orders, we could do a diagram like this, and then obviously I could put a melon here because we've said this is of order 1, this is of order now J squared, the n's cancel. This would be of order J squared. If I contract the indices this way, another J squared. But if I contract the indices in a different way, like this again is a J to the 4th diagram, you'll see that JKL has to be the same as JKM. And so the number of indices I have here to play with is just J, K, L, and M. That's n to the 4 divided by J squared n cubed squared, and that gives me a suppression by 1 over n squared. And so the final conclusion is the set of diagrams you have are gotten by taking this diagram and adding these bubbles on any line that you want. And these are called generalized melon diagrams. It's very different, it turns out, than just these vector diagrams. And not, however, as complicated as matrix diagrams. And in fact, you can write down a closed set of kind of algebraic equations that summarize the sum of these graphs. So if you look at the full set of one-particle irreducible graphs, some of which I've drawn here, you see that what we're doing is that every time we have an internal line, we're dressing it in all possible ways. So for this quartic interaction, the one-particle irreducible self-energy is a product of these three propagators in the time domain. This interaction, J here, in the Hamiltonian is independent of time. So if I draw these diagrams in time, this occurs at time tau, this at time tau prime. The propagator in tau space, in time space, cubed, is the self-energy. And that's what's drawn here. And then always, the propagator is the inverse of this geometrical series. The sum of the full propagator is the sum of irreducible, geometric sum of irreducible diagrams. So roughly this thing, which is 1 over omega minus sigma of omega. So this is a simple geometrical, algebraic expression, but in frequency space. What you see here, if you forget about time, work in 0 dimensions, this is just an algebraic equation, although quartic order, no longer quadratic, but you can solve it. Okay? A closed set of equations for the two-point function. That's characteristic of vector models, not matrix models. And having solved that, every other term in the 1 over n expansion, it can be calculated by a linear equation. Now, these equations are a little unusual because this is time and this is frequency. And so, in general, you cannot solve these equations, or nobody knows how to solve them. The model is generalizable to Q term interactions, where Q equals 4 was the original model, in which case here you'd have Q minus 1. And there are two cases which are soluble. One is Q equals 2, where you just have a mass term, and it's kind of a free, random mass, Majorana fermion with a random mass. That's kind of trivial. Or Q goes to infinity, which simplifies life, and which is you could solve this exactly. Otherwise, the solution is only known for deep in the infrared, where you can neglect this term. So in the free theory, which is just that of a free Majorana particle, you have here a one-dimensional theory. The dimension of the field chi is 0 by power counting. A propagator is just 1 over ddt, or 1 over the frequency. Added a term which is j, these indices times chi, and you see this from the point of view of renormalization group is an operator with dimension 0. So it's a relevant operator, and it begins to be very important in the infrared. And you get driven to the point where this is relevant, where this dominates the dynamics, and we have 4 fermions, so that 4 times the dimension of the fermion must be equal to 1. You get the dimension of the fermion starts out at 0 with a free theory and flows to infrared fixed point here, where this term is irrelevant. And now you can solve, because in the time domain, this just says that G times sigma is equal to a delta function. These expressions, these equations at the conformal fixed point are actually invariant under arbitrary time reparameterization. You can see that this theory is invariant. It has a 1 over ddt, so there's no metric here. If you make an arbitrary reparameterization of time, the ddt changes, but that's canceled by the integral dt. And the same is, of course, true here. If you transform chi, you transform t to some function of t, and at the same time transform chi of t to f prime chi of f of t, f prime to the 1/4. You take the product of 4 of these, the f prime will transform ddt to the f of t. So these equations have lots of solutions, since you can make an arbitrary reparameterization. If you choose any one of them, you've broken that reparameterization, one-dimensional gravity, down to the conformal group. Anyway, so the solution in general for very short times in the UV is just given by the free theory, where the propagator you can easily see in time, in the time domain, is just sine t. But in the infrared, corresponds to 0 dimension, just a number. Whereas in the infrared, the dimension goes to 1/4, and this should therefore behave like 1 over t to the 1/2, and this is the solution. You have a flow from this to this. That corresponds to delta equals 1/4, and for a Q-body reaction, the dimension is 1 over d. Now, you can take that solution and make an arbitrary reparameterization, as I've just said, and that's very useful because if you reparameterize time, I've taken to be the real line, to a circle by this transformation, you immediately get the finite temperature correlate function. And that's useful in analyzing this theory at finite temperature, where the partition function, where time runs from 0 to 1 over the temperature. Okay, so that's the free theory. Very simple, very straightforward. You get a conformally invariant fixed point. Reparameterization time invariance has been broken down to the SL2R, the 2-dimensional conformal group, and everything is hunky-dory. And as I said, in principle, that solves the theory from a nonlinear point of view. Everything else you do can be calculated, can be solved by linear analysis. Not that it's easy, but it's linear. And what you've done is flow to the point where this is the dominant term, and the fermion has acquired a dimension. Now, the 4-point function is the simplest thing to calculate, and you can easily see that that is equivalent to a linear problem by, again, looking at the graphs that dominate. So here you have a fermion coming in, again, because this quenched random coupling must be the same as this one. This index must be the same as this one, so the indices work this way, preserving SON. And the general diagram that survives for large n is just an iteration, a ladder of such diagrams, which means that you sum it once you know properties of this kernel. It's a linear integral equation for the full 4-point function. And this was solved by KITAEV originally, in schematic form, and then more detailed by Polchinski and Rosenhaus, and especially by Malissina and Stanford. And the most interesting way to analyze this thing is in terms of the OPE. So this theory, like in all these matrix vector models, we're really interested in the spectrum of gauge invariant or ON invariant operators. We have this theory of, this is an example of such an operator. But we can construct higher dimension operators, which in the free theory might be these guys, which are ON invariant. And in considering the scattering amplitude, which I just analyzed, I just discussed, we can try to sum these diagrams, but what are we really interested in extracting? There are two things we might be interested in extracting. One is the so-called out-of-time correlation function, which I'm not going to discuss, which has to do with the behavior for large times of chi I of t, chi I of 0, chi j of t, chi j of 0. Such a correlation function, which is so-called out-of-time ordered because you go from 0 to t and then back to 0 to t, is what you use to analyze chaos. That's not what we usually consider. We usually consider time-ordered products. And this is a little trickier, but can again is soluble by this linear technique. Okay. From the point of view of holography, what we're really interested in are the gauge invariant or ON invariant fields on the boundary in the quantum mechanical system, which somehow are dual to bulk observables. Sorry? I. And so we'd like to use our understanding of this 4-point function as a function of the various times, enter here, to pick out when tau 1 is of order tau 2, terms in the operator product expansion. So when these times come very close and these times become very close, this roughly product of these two operators can be expanded in terms of chi behaves like chi times chi, behaves like some operator of dimension something times 1 over tau 1 minus tau 2 to the dimension of On minus twice the dimension of chi. So if we examine this 4-point function in the limit where these points come together, we can pick out the OPE coefficients and the set of operators that contribute to the sum. And that's what was done by these authors. And you kind of expect that there will be an infinite tower of operators, which are roughly speaking these guys, with dimensions which are roughly speaking n plus 1, at least in the free theory. And at the conformal fixed point, should have dimensions equal to twice, n plus 1 plus twice the dimension of chi, plus perhaps some, in general, some anomalous dimension. And so the analysis of that linear problem is what produced the so-called spectrum of operators, which in the free theory are these. And they can be deduced from solving that linear problem, which is determined once we know the eigenvalues of the kernel. And one deduces such a formula for the various dimensions of those operators, which, as I said, should roughly be, the ones that actually contribute because of these are Hermitian operators are only even dimensions, only odd dimensions. Otherwise, they're total derivatives, they're not. So these are the primary operators in the theory, and they're, you see, equal to the dimensions of the, twice the dimension of the fermions, plus the number of derivatives, plus a correction which goes away or in the infinite limit of the spectrum. Now, this is somewhat similar to matrix models in ADS-CFT and SUN gauge theory, where again you have an infinite number of operators, all single trace operators, but there are many more of them. There are an exponential number of them as you increase the number of derivatives or the number of fields. And but there's a parameter that you can use, a marginal parameter characterizes the conformal fixed point, which is the coupling itself. UN maximally supersymmetric gauge theory in 4 dimensions is conformal for any value of the coupling. And for large coupling, most of the operators develop infinite dimensions, which correspond in the bulk to infinite masses, which corresponds to the fact that the coupling in the boundary is dual to, in a sense, Planck mass. So in the limit where the coupling goes to infinity, the splitting between the string states becomes infinite, and you're only left with a finite number of operators. This is a critical fact in analyzing ADS-CFT for matrix models, but it doesn't work here. Here you have a spectrum of operators that survive, and there's no parameter anybody has found to be able to push an infinite number of them away. So it means that all these operators will correspond to some degrees of freedom in the bulk, generally massive, except for the lowest dimension one, which is dual to gravitational degrees of freedom. And one needs to understand what the theory of those massive bulk excitations is. Now, there is a enormous subtlety in this whole business, because the lowest dimension operator, which you might think corresponds to a massless particle in the bulk, and the gravitational degrees of freedom, is rather singular. There are no gravitons in 2 dimensions. 2-dimensional quantum gravity is a little tricky. It shows up in the bulk, in the boundary, by having that 4-point function actually blow up, unless you include corrections that we've dropped in the limit of infinite times, 1 over tau corrections. And this is indeed reminiscent of things that happen in the boundary, which were analyzed over the years by many, many people, gravity in 2 dimensions, but more recently by Almeri and Bolshinsky. There's a very detailed story of that. And roughly speaking, it corresponds to the 1 degree of freedom that is what left in the gravitational theory that dominates the boundary theory in the infrared limit. So this is the model, a consistent model of 2D gravity with a cosmological constant, 2 here in units, and coupled to a dilaton, a scalar field, which is adjusted to have a particular value. And you see the equations of motion for phi are just the Einstein equations. So they really have here an ADS2 background as an equation of motion, but when you define the solution of this theory, you have to fix a boundary condition, and you have this picture, which is a beautiful picture taken from a lecture by Maldacena, shows that you have a freedom of defining the boundary condition on any reparameterizations of perhaps the trivial circle which you take towards the boundary. And that gives you that degree of freedom in the bulk is the dominant surviving degree of freedom in the infrared on the boundary, a function of tau, the action for which you can derive from both the bulk and Maldacena and Stanford did from the boundary. And action is given by the simplest action, which is invariant under SL2R, which is the Schwarzian. This is where the maximal chaos comes from, and has been shown, in fact, to be 1 loop exact. So it's a very simple degree of freedom corresponding to the gravitational degrees of freedom. Okay, now I really run out of time. I'm mostly what I've been mostly interested in about, not in these generalizations necessarily, or large Q limits or other generalizations, but in understanding the bulk theory. I should remark, and I think Vlad is going to discuss this in more detail, that this whole quenched random interaction and these melodic diagrams, the melodic diagrams which come from introducing a quenched random interaction, have been reproduced already in the literature by people studying so-called tensor models. You indeed might think that from after discussing large N vector matrix theories, you might discuss theories where the basic degrees of freedom have 3 indices or 4 indices, or in general, nth rank tensors. And people were motivated to do this by trying, for the same reason that the matrix model with 2 indices describes 2-dimensional geometry. The thought was that, well, let's study 3 index objects they might describe. We might be able to find Feynman diagrams that generate all 3-dimensional geometries. That's a tall order because three-dimensional geometries are not even, there's no way of counting them or classifying them very easily, and it failed by and large. Various large n limits were analyzed for example, for theories with three indices. With the indices, now you need colors, contracted in this way, and they didn't generate, they generated some subset of triangulations of three-dimensional geometry, but not in any sense full three-dimensional geometry. But the techniques that were developed for those tensor models have been very useful, as Witten first noticed, because the simplest tensor model with this way of contracting indices turns out, as those people realized, proved to be dominated by melon diagrams. So that meant that one could take these tensor models, not as models of 3D geometry, but to reproduce the SYK. So for example, this melon diagram, that was the first one we had, is just this way of contracting the indices. And you see you get 1, 2, 3 index lines, so that again goes like n cubed, just like we had here with the random couplings. And it's been shown that this works to all orders in the expansion, and if you take the leading, draw all the diagrams and connect these index lines, the diagrams that survive are exactly the melodic diagrams. This is, however, not a model with random quenched couplings. Here the couplings are fixed, and so it's much more like a quantum field theory with a permission Hamiltonian, and physically might make a lot more sense. It, in fact, does differ from the SYK model when you go beyond the large n limit. The 1/n corrections are quite different and more complicated. So if you're only interested in large n, and what we've been largely working on is the classical limit of the bulk theory, then you can take n to infinity and the two models are the same. But Igor Klebanov and others have been working on this new class of tensorial models, and they are much more complicated, but often much richer, since it's easy to generalize tensor models, take tensors now to be bosons or fermions, not just in dimension 1, but in any dimension, and it's a new class of large n limits of quantum field theory. Very rich. Okay. But the question that I've mostly been interested in, and which Vlad will describe in great detail our work on, is the bulk gravity / string theory that needs to be discovered. So here the goal is to assume that there is a holographic theory in the bulk which contains, that already has been shown, 2D gravity, but there are an infinite number of massive modes of something. This would be analogous to starting with ADS-CFT ideas, taking supersymmetric Yang-Mills theory, and discovering or constructing the critical string theory. Nobody's done that. Nobody knows how to do that. You don't know how to reconstruct string theory from the bulk. Principle, you know how to do it, but no, but I think it would have been extraordinarily difficult without knowing what that bulk string theory, not having solved critical string theory previously. And so we've been following this direct approach to try to take the degrees of freedom in the bulk, which are exactly these fields with the power of dimensions, and construct the 3-point correlation functions of that conformal field theory. Conformal theory, once you have a complete set of operators For large n, we do. And you know their 3-point functions. That's by conformal invariance given by group theory with numbers. Once you know these OPE coefficients, you've solved the theory. So in general, a bootstrap approach to conformal field theories is to write down a set of equations that relates these OPE coefficients and try to find solutions, or numerically, or bounds, and so on. Here we actually have quite a intricate quantum field, conformal field theory with an infinite number of local operators and OPE coefficients that we can calculate exactly. And we've done that. Once you know that, you can find the bulk theory that reproduces them. And that's not very difficult at the, if you want the so-called Witten diagram of a bulk theory whose boundary values have these OPE coefficients. That's pretty straightforward, and in principle, once you've done that, you have the point functions, you can, using the operator product expansion, construct the endpoint functions of these operators. And that we've explicitly more or less done. And then, in principle, you can use that to try to construct the endpoint functions. So at the cubic level, you have an infinite number of fields, and you can translate the OPE coefficients, which are easily calculable, not so easily, but calculable, in terms of summing Feynman diagrams like this, a linear problem, because this is just that kernel we solved, and construct the cubic couplings, and in principle, anyway, here are some of the answers. Let's see. Yeah, that actually is the answer of the 3-point function, which is a number which depends on the dimensions of the operators. And for that, you can extract and study the 3-point functions as a bulk. What's much harder are the endpoint functions, both on the boundary, which is completely soluble, and we've sort of outlined how to do that. So with enough work, you could calculate any endpoint function, but translating into the bulk is always tricky, because in general, a conformal field theory on the boundary yields a non-local theory at the bulk. You don't expect it to be local. There's no reason it should be local. Indeed, string theory, which is dual to gauge theory on the boundary, is not a local theory, not a local quantum field theory. And it's a string theory. So we have studied in detail the 4-point function. Here are some properties of the particular. This is not important. Yeah, is the 4-point function. So 4-point function on the boundary is quite calculable, and that's what we've done. Yes. And then you, in principle, can start discussing the multi-point functions in the bulk. But what you discover already at the 4-point function level is non-locality. There is no simple quantum field theory in 2 dimensions consisting of the gravitational degrees of freedom and an infinite power of massive particles that is described by a local quantum field theory. You don't expect there to be, because after all, string theory is not a local quantum field. Unfortunate thing here is that we don't know what string theory, we don't have a good candidate so far for that bulk, quote unquote, string theory or whatever non-local theory it exists. There are lots of possibilities. It's not too hard to get the spectrum. You analyze the multi-point couplings that we can calculate. They look kind of stringy in some ways. I don't have time to discuss. But it's still a big mystery. And I find it most fascinating because, in my opinion, the string framework, as I like to describe it, not a theory, it's a way of constructing quantum gravity theories, but one thing we're sure of is that we have no idea whether the methods we've used to construct string theories so far by any means exhaust the full set of string theories, particular string theories. And this very well might be a totally new class, much in the way that Vassiliev gravity is a new class, one that's very hard to understand and worth study. And Vlad will fill in the details, especially of the last part of this, and take you up to the frontiers of our knowledge, which, as you will see, are quite extensive. But that's good, because it means there's a lot of stuff for all of you to work on if you want and to figure out. Thank you.
Thank you very much. Yeah, maybe we'll have a couple of questions. Spencer.
David, this is a no-brainer question, but let me ask it anyway. Is it possible to organize these infinite number of fields that you just mentioned and write down some sort of a some sort of a string field theory?
Yeah, I mean, I'm sure. What is a string field theory? A string field theory is one of our only known examples of a non-local quantum field theory, if you want. It's better described as a string theory. So there are obvious ways of trying to go about doing this, which we and others have tried so far. And, you know, we have very severe tests, since we can solve the theory completely in the large N limit and have, for all the endpoint functions, there are lots of ways of getting the spectrum. But, you know, a string theory in 2 dimensions is a little strange. String theories typically have the only physical degrees of freedom are the transverse modes. There are no transverse modes in 2 dimensions. So it's possible that one thing we have been exploring are longitudinal modes of strings, which have been analyzed over the years in many different ways. They're very tricky. There are other approaches, compactified strings from higher dimensions. Trouble is, we don't see any sign of Kaluza-Klein modes. But I don't know. This is a wonderful challenge, because in the world of string theory, non-local theories that include gravity, we were kind of lucky to find flat space critical or non-critical first and then critical strings. Very simple 2-dimensional field theories that we can analyze. And were discovered, therefore, sort of accidentally, as you know, dual resonance model and so on. So this was just a kind of dumb luck that physics often has of the existence of very simple integrable limits that are not so far from the real world in some circumstances. So hydrogen atom. So now we have something which is soluble, and we have to find what it's dual to. And as I said, you know, if you hadn't known about critical string theory, you would have found it pretty hard to reconstruct string theory from the large N limit of QCD. Or we don't know how to do it for QCD, in fact. There's another challenge. Large N limit of QCD is surely some kind of string theory. And boy, would it be great to know what that limit is. what the classical theory of QCD strings is. But this case is a little simpler and very explicit. So I'm sure somebody will figure out how to do it.
Jungi.
Hi. I have several questions. First one is the usual one. Just what is the play role of the random coupling constant in the holographic dual? And the second one is like in non-planar diagram in matrix model, what will be this role of the non-melonic diagram in this holography?
Well, there are 1 over n corrections. As I said, so, you know, the non-melonic diagram, the other terms in the 1 over n expansion will correspond to interactions of this classical theory. Loop corrections is classical theory. So, of whatever it is. And you can, it's a totally straightforward task to do 1 over n corrections to any large n limit. That's, again, a linear problem. And the same, of course, is true in string theory, or in any quantum theory. Once the large n limit in the bulk will be a classical theory of some non-local object, some non-local classical theory. But once you know the Lagrangian, or the, you know, then you know how to construct loop diagrams. It's totally straightforward. So you won't learn anything. Here the problem, you won't, I mean, you'll learn something about 1 over n corrections if you're interested. But here the problem is just to understand the classical limit.
Okay, I think we should close now. And on my side, I would like to really thank David in the midst of this very punishing schedule that he had to given such a brilliant lecture. And especially with the blackboard, it brought back memories of from 25 years ago.
Brought back memories of running into lunchtime. Right?
The 2.5 hour long lectures that we used to have on quantum field theory. But thank you, David, again. And I forgot to mention at the beginning, I said the Kavli Foundation is supporting the winter school, but this is the Kavli distinguished lecture that we are having as part of the winter school. And so for that, we have a small memento and as a token, and I would like to invite Spenta to come and hand it over to David and conclude this distinguished lecture.